So to get started, what are containers? So you can think of containers as a kind of units of softwares that encapsulate an isolated environment for a single application or a bunch of applications to run independently from what the host machine looks like. You can also think about that as, say, a full directory tree with directories and files, so a file system similar to what you have in all of your computers, except that this directory tree is completely isolated and able to be used independently. And so that's how you guarantee that your application will run regardless the setup of the machine you're using. So where can you run these isolated autonomous pieces of software? Well, almost everywhere, any hardware, almost any operating system, and so any site really, and any user can use the same container with really no big change in the way they operate it. The container technology was started a few years back in the IT and enterprise world, but in the recent years has become increasingly popular in the HPC world as well, so scientific computing. You might have heard of virtual machines. So just to add some points to the description of what containers are, we can make some parallel between containers and virtual machines. So VMs are a software tool that is able to virtualize the entire hardware of a machine. It means that it provides a piece of software that is able to abstract what the real hardware of a computer is and interface then to any type of computer you might use on top of. This means that this virtual machine needs to ship with the entire operating system, including the kernel, which is the core unit that makes any operating system work. But this also implies that virtual machines, because of their nature, are quite heavyweight to run. So they take a lot of resources in terms of RAM, compute power, and disk space. And it also takes some time to start them up and shut them down. On the other end, containers don't really care about, they're not able to, say, to handle different hardwares. They don't care about that. They don't deal with that. They only virtualize the operating system. It means they're able to interface with different operating systems without caring about the hardware. So what it means is that they basically share the same kernel, the same core of the operating system of the host, and they just build on top of that. And this might just suggest you this key aspect that containers are much more lightweight than VMs. It means they take much less resources to be run, so less compute power, less RAM, less space. And also they can be started and stopped very quickly. So this makes them a bit more ideal for high performance workloads where you don't want to waste precious compute time and resources just in starting and stopping the infrastructure that you use to run your applications. So the key tool that you need in order to run containers is then a container engine, which is exactly this piece of software that is able to make your container live. So to bring this isolated file system, put it on top of the kernel of the core of the host operating system and make it work regardless the machine you're working on. There are a few options available out there. So Docker was the very first solution that was developed, and it's really quite common and widespread in the IT world. It's good on PC, workstation, even on cloud. A newer solution is called Podman with similar features. But then when you go into the HPC world, you need some additional care, additional features to be included in the design of these container engines. And so here we have slightly different options. So here I'm just mentioning a few: Singularity, which will be the core of this webinar, Charlie Cloud, Shifter, and others. So these container engines are quite good to be run on HPC sites, but also on cloud and eventually workstation. So they're still quite flexible in terms of where you can run them. So why using containers in scientific computing and HPC, so including bioinformatics? Well, this technology allows us to enforce some good practices in running scientific workflows. And in particular, today, I'm just spending some words on reproducibility, portability, scalability, and I will also be touching on some aspects of productivity in a couple of slides. So first, reproducibility. So the matter here is we often, researchers need to run their analysis multiple times. You need to repeat them. And hopefully you wouldn't need the results that you obtain from the same inputs to be the same over time. So say you repeat the same analysis in the same machine, maybe with a different software setup, because meanwhile upgrades have been done, right? Or you want to run your analysis or need to run your analysis on different machines or sites. So here we're talking about portability. Or you need your analysis to be run by other people, maybe your collaborators or some peer reviewers of your publications that need to double check your results. So here we're talking collaboration and shareability of your analysis. Containers are very effective at enforcing this, because by nature, as we said, they provide the entire software environment to run application as embedded in a single piece of software that you can run and you can ship and run everywhere on any machine. And this also has some quite specific advantages. Say, if you have software stack with a lot of dependencies, I'm saying just for instance, R Python workflows, but also other ones, it might become quite difficult to be able to version track all of the software you need to run your application. And in containers, you can achieve that quite easily because you're shipping everything all together at the same time and you're not changing the software stack once you have first installed it. You're just basically redeploying the same piece of software in different sites. Then we have some scalability aspects. So you might have happened to you that you start and work on your laptop or on an office workstation, and you only have small samples. Then the amount of data grow, and you need to move your analysis to some other place. Might be an HPC, might be cloud. Well, the good news is these containers, these isolated pieces of software, can be shipped around on different machines, but also they can be scaled up to run at the same time on a large number of nodes, which means if your analysis really grow up in scale, you can very easily and natively run these pieces of software at scale without any change in the installation, which means we're saving quite a lot of time. And this is ensured, again, by design of the container runtimes that have been designed for HPC, such as Singularity. And then we have some productivity aspects. So I've heard stories of researchers spending literally weeks of their PhD, if not months, just to install software time. With container, you tackle this very well, because basically you solve the problem of installing your software once and for all. And then all what you need to do is basically to just ship or download the installation on a different machine and you're good to go. And very often you'll find that the software you need has been already containerized by other people. So you don't even need to bother in installing it. It's basically ready to go for you. And this also includes all the software where just installing the dependencies, the prerequisites, takes a lot of time. Again, you solve that once and for all, and then you don't waste any more time just in installing packages. So how do you normally use containers? The starting point often is some web registry, so some public repository, which you can find on the internet, that collects containers that were built by other people. And these are just a couple of examples, Docker Hub and Key.io. If you look for your software there and you find it, well, all you need to do is literally to download it on your system and you're ready to go. And this happens, honestly, quite often in bioinformatics. We'll get back to this aspect later. The alternative, if you don't find the software you're looking for already in container form, well, you can spend some time in installing it in a container, so in building a container image. And then again, once the image is ready to be used, you will deploy it on your production system and use it for your analysis. Who is using containers at Pawsey? Well, right now we have a growing community of users of this technology. I'd say the biggest one is possibly bioinformatics, but we also have machine learning specialists, Python users, computational fluid dynamics engineers using OpenFOAM. And we also have people deploying RStudio and Jupyter sessions using containers. The software tools we're using are Singularity in our HPC, so you will find it pre-installed on all Pawsey systems. And as regards the Nimbus Cloud, so Pawsey Cloud system, we also provide Singularity pre-installed in all virtual machines, but we also install Docker, and we'll get back to the reason for this later on. So just some definitions before we get started with the hands-on session, because I'm going to use these words quite often. So we call image the actual shipping unit of containers. So think about the image as the collection of files that make your application work. This is the unit that we are shipping around, so we are building it before we use it. We are looking for it in a web registry. We are downloading it on the production system. This is the image. Whereas to be picky and precise, the container is a slightly different entity. The container is the actual instantiation of an image. So it's the process that you can spawn out of an image. So think about the container as the running application, as the open application that is carrying out the actual work. And then we have the registry, which is a place to store and share container images. There are a lot of public registries available out there, such as Docker Hub and Key.io, but you could also eventually build private registries if you need to ship software that can be shared with everyone. And finally, we have the Docker file of definition file, which is basically a specification for when you need to build a container image. It's basically the recipe that you use to build a container. And so just before I stop for a couple of minutes for some questions, let me just show you graphically how these web registries for container images look like. So this is the library from the Singularity authors. It's called Scilab Singularity Library. Here is the field where you can actually look for container. And so Singularity Cloud is not really interesting. It's quite recent, and right now the uptake is quite low, so it's not that interesting besides being shipped by the same authors of Singularity. Docker Hub is much more interesting. Here you can find a lot of starting images for when you need to build containers. So it can be operating systems such as Ubuntu, be Python, and basically use these search fields to look for containers. And then there is a third one that it's particularly worth mentioning with a bioinformatics audience, which is Key.io. And the reason for that is that you might have heard of Bioconda, which is a project to provide a package manager for bioinformatics packages. Well, Bioconda has also recently started a project called Biocontainers, which is a porting of all Bioconda packages into containers. And Key.io is the place for look for biocontainers. So say if you're looking for BLAST, high chances are you will find it in Key.io as built and made available by the Biocontainers project. And it is, say, item number 2 in the search list. So basically, I think there are literally several thousands of bioinformatics tools available in Key.io. So that's your first destination for every time you want to use containerized bioinformatics applications. So that being said, I'm just stopping for a couple of minutes in case there are any questions on this first part of this webinar today.
Okay, thank you, Marco. And we do have a couple of questions. I'll pose 3 if we have time. Why Singularity in Docker? And there's a bit of conversation going on about security.
Yeah.
So.
All right. So, well, I will mention quite soon, basically in the next slide, why we are picking Singularity and not Docker. So, and maybe I will also mention a bit on security when I get there. So
great.
Hold on just a couple of minutes.
Okay.
And thanks for the question.
Another question. Can Singularity be used on a PC/workstation?
Yes. So actually, at the end of this presentation, I will share with you a link to the GitHub project that is behind the tutorial today. And there I provided instructions for installation of Singularity basically on a Linux system, on a Ubuntu OS. So that can be considered as a template for installation on Linux. So basically installing Singularity on any Linux system is quite straightforward. You need root privileges, so you need to run the installation with sudo commands, which means you can't install Singularity yourself on a shared system such as HPC. Administrators need to do that. But if you have sudo access to a machine, you can install Singularity quite seamlessly. For Windows and Mac users, the best way to install Singularity right now is by using a tool called Vagrant. You need, again, root privileges. But again, I provided the installation instructions on the GitHub page of this tutorial. So stay tuned for that.
Okay. What will be more lightweight in terms of disk space and loading time? A Conda environment or a Singularity container?
I say possibly for a lot of applications might be similar. My take is that with containers, basically containers are a more general tool compared to Conda, because with Conda, you're basically restricted to be able to install software that is already available on Conda, whereas with containers, you can basically ship whatever you want, including Conda packages if you wish to, but you're not restricted to that. And personally, what I like more about a container shipping compared to a Conda environment is that it's more easily reproducible. Well, you can, with Conda, you can as well save and freeze your installation stack at any given time and just reinstall the same one again. But you need to be willing to document that yourself. Whereas with containers, by design, you get 100% reproducibility on the software stack. So you will be always ensured that if you run the same container image, you will be running exactly the same piece of software file by file.